All right, next up we got Kira. Kira is the co-founder and CEO of Líta, a materials startup developing microwave-assisted manufacturing processes to produce high-performance materials used in tooling, aerospace, and lithium-ion batteries. Kira earned her PhD in materials science from UC Santa Barbara and recently raised a $4 million seed led by Voyager. So here we go.
Awesome. Well, it's so nice to be here in San Francisco. Thank you, Nare, for the introduction, and I'm very excited to share more about what we do at Líta Materials. So at Líta, what we're really focused on is unlocking industrial materials that really matter. What we're doing is revolutionizing the production of these fundamental industrial materials. And when we think about the types of materials that we're looking at, these advanced industrial materials really underpin the technologies we use every single day. And we all know this from our phones, cars, solar, everything we touch is based on a material, and specifically these very important advanced industrial materials. So examples are hard materials in tooling, active materials in lithium-ion batteries, electronic materials, advanced coatings for aerospace, and a host of defense applications as well. And there's sort of two really big problems. So one of the big problems for these materials, they're also known as functional inorganic materials, is the underlying manufacturing of these materials has not changed significantly in over 132 years. And there's a lot of problems there, right? Technology has advanced so far. We're using so many advanced new pieces of technology, and yet we're still using extremely dated manufacturing for these materials. And so there's a huge opportunity for innovation in the actual manufacturing of these materials. The second really important problem here is that the current manufacturing processes were designed for materials, right, 100 years ago. And so even there's a host of very exciting next generation materials, but if they're not compatible with the legacy manufacturing, then they're basically, not usable in current technologies. And so that means we're limited to materials that are only compatible with these, legacy processes. So what we're doing at Líta is really developing a next generation of manufacturing for these materials using an advanced microwave-based process. And so we enable sort of four huge advantages in the manufacturing of these materials. One is speed, so how fast can we make these materials? Quality, we are making the most sophisticated platform for manufacturing these types of materials. Affordability, how can we drive down the cost of some of these materials and also drive them down in a way that it's still economical to produce these materials domestically in the United States without tariffs or subsidies. And last is sustainability. We're really focused on performance, but we can manufacture these materials simultaneously in a much more sustainable fashion. And so let's talk a little bit about the physics of why we can do this. So I'm first going to talk about how current materials are made. And so typically these materials are made in what's called a rotary kiln. And so in this scenario, a kiln is heated from the outside, and this heat is transferred into the materials it contains. There's a lot of problems with this type of approach. There's huge temperature variations, there's inconsistencies in the material quality, and very poor process control. So you can think of this like a big thermal reservoir, right? You can think of your home oven, for example. Think about if you wanted to change that temperature by 5 degrees instantaneously. You cannot do that, right? And so making these industrial materials is not trivial. They require, for the highest level of quality, perfect control of the temperature, of the ramp rates, of the dwell times. Not possible. This leads to poor batches, lower quality, big problems from an economics point of view for manufacturing these materials. And so what we've developed is a microwave-based approach. This is fundamentally different physics for how we heat these materials. So instead of heating from the outside, and also I forgot to mention another important problem here, it's called a hot wall. basically, there's an optimal conversion temperature for these materials. If you want to heat them in a reasonable amount of time, then you have to heat the kiln hotter than the optimal conversion temperature, also a problem. We get around this by directly coupling microwaves to the material itself. And so when we do this, we get much more uniform temperature gradients, much more rapid heating, and also now we unlock the possibility of actually precise process control, which was just not possible with sort of legacy thermal transport. And so overall, what we're really doing is significantly boosting the overall efficiency of this manufacturing process. So we're reducing the manufacturing time quite significantly by up to 99%. We're reducing cost significantly for some of these material classes, and we're also decreasing the energy usage. And so by leveraging a fundamentally improved physics mechanism for heating these materials, in conjunction now with best-in-class manufacturing automation, we significantly boost overall efficiency of these processes. And so our business model is selling premium powder directly to product manufacturers. So just as Rowan was talking about with Earth AI, mining, discovering these important metals and different materials, we take the materials that Rowan is discovering and we process them in our proprietary process into very high value materials that then we sell to product manufacturers that can make their parts. So this could be a drill bit, for example, maybe a lithium-ion battery, different electronic wafers, for example. And what we've really demonstrated is that we've developed a platform technology that will enable us to onshore these important manufacturing processes. I'm highlighting a number of examples of materials that we manufacture: hard materials, electronic materials, battery materials, which each have their own value propositions with our technology. And I'm really going to focus today on the hard material market. Hard materials are so integral for so many important applications. Rowan was also talking about drill bits, for example, or mining bits, very important for the entire base of the mining supply chain. The hard materials really underpin so many important applications: mining, machining, defense, a variety of energy applications. And a lot of these applications have been dependent for decades on tungsten carbide. The problem here is that there's been really very small amount of innovation in the materials used in these applications. So if we take a mining bit, for example, a mining company can maybe change the geometry of a bit. They can maybe put on an advanced coating. But at the end of the day, it's that base material, the base tungsten carbide, that dictates the maximum ceiling of performance. So the only way to improve the base performance and get a step function improvement in performance is upgrading that base material. And so at Leeta, we can manufacture currently used industrial materials much more efficiently, but we can also basically unlock a new class of hard materials that finally allow these companies to get the next step function in performance. And these materials are called tungsten boride materials. And these materials offer significantly higher performance than traditional tungsten carbide. For example, some of the benefits include longer life, lower wear. This can lead to a host of benefits such as shorter downtime, higher oxidation resistance. And the reason these materials aren't being used yet is because they are not compatible, the manufacturing of these materials, with legacy heating. Two important requirements for introducing better materials, right? It needs to be scalable and cost competitive. And this is what Leeta unlocks with our microwave platform. And so just to sum it up, we're very excited at Leeta to bring this important material manufacturing back to the United States. Thank you.
Sorry, you have to bear with me. I've lost my voice. So thank you so much. This was a great presentation. You made it sound so easy peasy, which I appreciate. But I'm wondering what's the main technology enabler, because probably so many people thought about this but couldn't make the breakthrough. in this like microwave technique?
Specifically for the actual materials or the microwave processing?
The microwave processing.
Okay, so the question was regarding, I guess, why hasn't microwave process... Could you repeat?
What was the technology enabler that you could use microwave processing and nobody else
Sure.
couldn't so far?
Right, so the question was, why can we harness this microwave technology and it hasn't been done before in this way? It's important to note, microwave technology is very well established, right? Microwaves have been used for many decades and are used in a host of different industrial processes. This ranges from food sterilization, like jam, chicken cooking, wood drying, for example. And so there's already examples, industrially used large-scale processes, continuous processes, using microwaves. But there's a big difference with those processes than what we're doing. So one of the two important differences than what's been done already is basically the temperatures we're operating at and the sophistication required for the highest quality materials. And so a lot of the current processes are significantly lower temperatures. These are high temperature solid state reactions, which require a lot more nuanced understanding of how to design the reactors and processes themselves. And they're much less forgiving than traditional, let's say, just evaporation processes. These are much more sophisticated reactions that require really materials know-how to be able to access this properly.
Thank you. That was terrific. I was curious what materials specifically, do you have intellectual property protection around the creation of a certain, is it just tungsten carbide? Is it multiple materials for your process to be able to use the microwave technology to create?
So the question was regarding what are the types and breadth of materials?
Yeah, the intellectual property protection that Leeta has.
So specifically more, okay, so the question was about the IP.
Yeah, and applied to which materials? I hope that was, thank you.
Okay, so sort of what materials can we really make? What we've proven in our reactor today is basically across the board, much more efficiently make almost every single currently used industrial material. So these classes of materials are oxides, carbides, borides, and nitrides. Yes, and so under the umbrella of these materials are also very high performance battery electrode materials on the cathode and anode side.
Hi, Kira. Thanks for the interesting talk. I had a few questions. Mainly one is, I imagine the complexity of building these reactors, as you were saying, is non-trivial. And so at what scale is your next step to build these structures? And more specifically, I also imagine that the process is very material specific, like microwave absorption is different for a certain material from another. So what is your first target for this type of technology?
Yeah, so the question was regarding sort of the first target for this technology and the scale. Sort of to answer this in two parts. So one, it's not trivial to design these systems. We leverage advanced physics-based modeling to really create our reactors. Already today, in the generation of reactor online with our boride materials, our reactor is basically able to produce up to 4 tons already annually of some of these boride materials per year. Our next system that we'll be bringing online, kickstarted by Voyager's investment in us for our seed round, will bring online the next reactor that can produce 34 tons per year, and we're primarily focused on tungsten boride.